Congratulations, if you're watching this video, that means you have almost made it all the way through Chapter 6. This is the last section of Chapter 6 that we're going to be covering before the test. And as the title says, this section is about graphing radical functions. So it is going to pull in some of the ideas that we talked about in the last section when we were covering inverse functions. So first of all, let's talk about the graph of f of x equals x squared. Obviously, that's not a radical function. That is a parabola that we've already studied. And the graph of f of x equals x squared looks something like this. Now, if you recall from what we said in the last section about inverse functions, we know that the graph of the inverse of f of x is going to be the reflection of our original function over the line y equals x. So if there's my line y equals x, then the graph of our inverse function, let's see, I'll graph that in purple, will just be a reflection of our parabola. So this first branch to the right, this guy right here, that's going to get reflected over our line y equals x, and that'll look a bit like this. And then our branch on the left, right here, that's going to get reflected over our line y equals x, and it will end up down here below the x-axis. Also, related to our last video, we talked about the fact that sometimes the inverse of a function will not also be a function. And that's the situation we have here. We could use either the horizontal line test on our original function, or we could use the vertical line test on our inverse function to prove to ourselves that our inverse is not also a function. So let's just run the horizontal line test on f of x equals x squared real quick. If I pass a horizontal line over our original function, notice that line passed through our function in two spots. And that's what tells me that our inverse function is not also, our inverse relation, is not also a function. Or we could use the same reasoning to use the vertical line test on our inverse relation to show ourselves that this inverse relation is not a function. But that we do want to have some sort of inverse function that we can work with when we're talking about our parent function f of x equals x squared. So what we actually do is we're going to restrict the domain on our original function so that when we're talking about the inverse of x squared, we're only going to be talking about this positive branch right here. So here's what we're going to call f inverse. And of course the inverse function, if our original function is x squared, that's just the square root function. So when we're talking about the graph of a square root function, we're only going to be referring to this single branch right here. And again, the reason we only talk about that positive branch is so that we force it to actually be a function. So let's talk a little bit more about this graph of our function square root of x. We just said that if we were just talking about the parent function square root of x, then it is only going to have one branch and it'll look a bit like this. Just as with any other graph, we can perform various transformations. If we wanted to graph negative f of x, of course that's simply a reflection. So that would reflect our original function over the y-axis. Some other things that we can do to our function would be to stretch it. We've talked about stretches before. So a stretch would be something, well, it would be when we are multiplying our function by some constant. So we could write that as a times f of x. And so stretching our function, depending on the value of a, will either make it come up like that, or get it closer to our x-axis. Another type of transformation that we've already talked about is a stretch, a shift. So that would mean that we are taking our original parent function f of x, and perhaps if it was a vertical shift, we would be adding a constant on. So that would look something like this. Or perhaps we are shifting our function from left to right. Remember, that affects the x coordinates only, so maybe it looks like that. And in that case, if we're only shifting from left to right, our new function will look something like this. So these are all ideas that we've already talked about in relation to other types of functions, but we're just applying these same ideas of transforming functions to our square root function. Another type of radical function that you need to be familiar with is the graph of the cube root function. So let's take a look at our parent function for this, the cubic function, which we've already studied a bit. We talked about that back in our chapter about polynomials. So if this is our function y equals x cubed, we should hopefully be familiar with the idea that the inverse of the cubic function would be the cube root function, because whatever you cube, if you take the cube root of that, you get back to what you started with. So just like with the square root function, we can find our cube root function by just reflecting, that's not a very good line, reflecting our cubic function over this line y equals x, since the cubic function and the cube root function are inverses. So that means that if we take our branch from the origin up and we reflect that over our line y equals x, we'll get something that looks like this, and it should look, that branch should look very similar to the square root function. And then if we graph the reflection of our lower branch over this line y equals x, we'll get something that looks a bit like that. So it's probably a little hard to see. I'm going to erase what I've done so far and just graph our cube root function for you. So say goodbye to the cubic function. Here is just the cube root of x. This looks a little better. There we go. So there's a positive branch to it and a negative branch to it. Now with the cubic function, we don't need to worry about restricting the domain, because if you notice, if we perform our vertical line test on this function, I can pass any vertical line over our function that I want, and it only touches our function in one spot. So the cube root function, f of x equals the cube root of x, does pass the vertical line test. So there's no need to restrict the domain here. We can generalize this statement. If you remember back to our polynomial, I'll leave it here. If we remember back to our chapter on polynomial functions, we talked about how the degree of the function would influence the overall shape. So I'm going to just sketch this up here in the corner. And we said that for any polynomial, if the degree was even, then our overall shape would look something like a parabola. So if it was a quadratic, it would look like that. If it was a quartic, meaning the degree was 4, its overall shape would be what you see here in orange. So any even degreed function would look a bit like that. And then we also said if the degree was odd, then our function would look in general like a cubic function. So one branch would be going up, the other branch would go down. The same sort of generalized concept applies when we're talking about these radical functions. If your index, remember that's the little number above your radical sign, if your index is odd, then your overall function is going to look something like this cube root function. So if you're trying to graph the 5th root of x, or the 9th root of x, or even something crazy like the 27th root of x, because all of those indices are odd, the general shape of that function will look something like this cube root function. However, if you were going to graph something like your square root function, let me get rid of some of this stuff for you, then that would mean that your index of your radical function would have to be even. So something like the 4th root of x the 8th root of x, the 16th root of x. Any even indexed radical function, its overall shape will be something like this square root function, where it will only have that one branch because its domain had to be restricted. Okay, let's do a few examples. Let's say that we want to graph this function, the 3 times the square root of x plus 2 minus 4. So you need to be thinking back to those transformation ideas that we talked about earlier in the year, so we can see what's going on here. If we're multiplying our square root function by 3, we're multiplying by a constant, so that's going to be some type of stretch. If we are adding 2 underneath the radical, that's going to be a horizontal shift. And then by subtracting 4 outside our radical expression, that's going to be a vertical shift. So you just have to remember that the position of these various constants determines how it's going to affect the graph. Adding or subtracting means that we are shifting either horizontally or vertically. When you're multiplying by a constant, that means that you are either stretching or compressing your function. Okay, so let's talk about what's actually going on in this particular example. So first of all, what I would do is I would identify what your parent function is. Since this is a square root function, that means that, of course, our parent function is just y equals x squared. Or, excuse me, y equals the square root of x. So that's the parent function that we'd be starting with. Then let's talk about what we're doing to that parent function. This value under the radical sign of x plus 2 means we have a horizontal shift, and you do need to remember that a horizontal shift acts on x using the sign that is opposite what you see in the expression. So if we're adding 2 to x, in this case that actually means that we are shifting 2 units to the left. So we're taking our parent function, and first we shifted 2 units to the left, so that's going to be somewhere around here. And then on the outside we are subtracting 4, so that's a vertical shift 4 units down. So that means we've now, if we're moving 4 units down, we're somewhere around here. And then finally, if we are multiplying by 3, this is where you have to think back to what that the value of that constant is going to do. If you have a value that is greater than 1, that is actually going to shrink your function a bit. And if you have a value that is between 0 and 1, that is going to stretch your function a bit. So because 3 is greater than 1, we actually have a shrink here. So I'm just going to go ahead and erase what I've done and just give you the overall view. So we said we shifted 2 to the left. So there's -2. We shifted down 4 units. There's -4. So here's my starting point. And then again, this is just a rough sketch, but we're doing a shrink because we're multiplying by 3, so our overall function should look a bit like that. Okay, let's do another example. This time we're dealing with a cube root function. Again, you need to pay attention to that index. So our parent function is going to look a bit like this. So that's where we're starting, and now we need to take a look and see how we are shifting this around. First of all, we've got x minus 2 underneath the radical sign. That means we are shifting our parent function 2 units to the right. This looks a little bit different from our last example, but because the 3 is on the outside, it's being added, so that means we are also shifting our parent function 3 units up. There we go. Oh, that's a little too high, isn't it? That's better. 2 other things that we need to notice. First of all, we've got this value of 1/2 on the outside of our cube root sign, so that means that we are going to be stretching our cube root function, since 1/2 is between 0 and 1. And finally, because we're actually multiplying by a -1/2, we are also reflecting our parent function. So if our parent function looked a bit like this, when we reflect it, the new version's going to have to be reflected over the x-axis, so it's going to look something like that. Okay, let's put all these pieces together. So we shifted 2 units to the right and 3 units up. So that means I can put in my starting point. Oop, that was ugly. Try that again. There we go. There's my starting point. I'm going to be reflecting my cubic function, and I'm also going to be stretching it. So our overall transformed function is going to look a bit like that. Okay, I've got just one more example for you. Now here again we've got another cube root function, but notice this isn't written quite in the form that we're used to. We need the coefficient on x underneath that radical sign to be 1, but right now it's 8. So before we can even start graphing this, what we need to do is try to rewrite this equation so that we can put it back in our standard form, and then we can easily graph it. So the first thing I'm going to do is I'm going to notice that underneath the radical sign I can factor out an 8. And when I factor out an 8, that gives me 8 times the quantity x plus 4. This is helpful, especially in this problem, because since we're taking a cube root and 8 is a perfect cube, we can take the cube root of 8 and get 2. So I can pull that 2 outside the radical sign. So I just simplified that radical expression like we practiced earlier in the chapter. And we're left with 2 times the cube root of x plus 4 minus 2. And now our equation is written in a form where we can pretty easily see what's going on with this transformation. So here are my axes. Since this is an x plus 4, that means I am shifting my function 4 units to the left. Because it says minus 2 on the outside, that means I'm shifting it 2 units down. And finally, because we are multiplying our function by 2, that means we are compressing it. And so now I can go ahead and sketch my graph. There is no reflection here. So if here's my starting point, my function is going to look a bit like that.